Hello, we are going to start chapter 10. This is a continued section from the previous chapter, hypothesis testing. So, in chapter 9, we learned the basic mechanism for hypothesis testing, how we set up hypotheses and and how we make the decision, what is the significance level, what is the rejection region, t-stat, p-value, these basic things. But still, there are more things to discuss. For example, in this chapter, we particularly focus on two major topics. One is how to evaluate the accuracy of a hypothesis testing. I briefly mentioned in the previous chapter about the potential error, right? So in the example of finding abusers, it is possible that innocent customers can be banned, recognized as an abuser if they are unlucky. That is possible. So that is error. So we are going to calculate the probability of those errors. Okay. And second, in the previous framework, in the previous chapter, the framework is limited to the case where the null hypothesis is the expectation equals something. But in many cases, we are curious about whether the mean is greater than something or not, right? So, actually, this is more common. Null hypothesis with inequality is more common and could be more important. So, we are going to extend our framework to accommodate inequality hypothesis, inequality belief using inequality. Okay. So let me start the first topic first, right? So back to the example of the presumption of innocence, right? So in a criminal trial, the null hypothesis is innocence, right? The defendant, we have to believe that the defendant is innocent until it is certain that the defendant is guilty, okay? So that is kind of unneutral. It is biased decision-making process, but that is more natural in many examples. I gave you some examples, right? And here in this decision problem, we need to choose one of the two decisions, whether you reject the null hypothesis or you don't reject the null hypothesis, right? When you reject the null hypothesis, that means you determine that the defendant is guilty, so you are sending the defendant to jail. But if you do not reject the null hypothesis, that means you could not find enough evidence showing that the defendant is guilty. So you are going to set free the defendant, right? So this is basic, dichotomous decision-making process we need to handle in hypothesis testing. Then we are going to think about error. Like your decision could be wrong. That depends on the relationship between your decision and the truth. For example, think about two possible truths. First, the truth could be innocence. The defendant is actually innocent. But of course you don't know the truth, so your decision may be correct or not, given the truth. On the other hand, the defendant may be actually guilty, right? Of course you don't know, the statistician do not know the truth, so she can make correct or wrong decisions. So given the truth, we can see if the decision is correct or not. So that is what we are going to do in here. So depending on the truth, if the defendant was innocent, that is the truth. If you happen to know the truth, like maybe after the decision was made, then we can tell if the decision was error or correct. If the defendant was in jail at that time, when you realize the defendant was actually innocent, then you learn that the decision was an error, right? But could be correct decision. And vice versa. If the defendant was guilty actually, so like many years later, you may correctly know that the defendant was actually guilty, then you can check if the decision was error or correct, right? If the defendant was set free, then that was an error. This is possible, statistically possible because of random errors. So anyhow, we are going to calculate the probability of these two types of errors. So two types of errors in statistical terms, you can write it this, you can say it this way. If the null hypothesis was true, which means the defendant was innocent. If the null hypothesis was true, but if you rejected the null hypothesis, that is an error. We call this type 1 error or alpha error. I don't like this naming, by the way. So type 1 and type 2, there is no reason why it is 1 and 2. So even myself, I'm confused quite often. So but that's the convention. Anyhow, given the truth, if the null hypothesis was true, then rejection is an error, right? But if the truth is that the null hypothesis was wrong, then rejection is a correct decision. But if you fail to reject the null hypothesis, that is an error, right? So that means you could not find, so actually the defendant was guilty, but you could not find the evidence and you could not send the defendant to jail. So that is called type 2 error or beta error. So in this course, and many textbooks use type 1 and type 2 errors. I think that's more common terminology. So I will call them type 1 or type 2 errors, right? So then let me summarize the idea using graph. Here, the null hypothesis say is on a line. You believe that the true population mean is here, mu 0. You believe that the mean is here. So you are collecting data. And that means before collecting data, what you're going to do is, so your belief is mu 0, and that means if your observation is further from the belief, you think it's more suspicious, right? If the evidence is further away from your belief, then suspicious, right? So you decide rejection region based on this rationale, right? It will be more suspicious as the evidence data are outside, right? So you determine the rejection region first. When the data sample mean is far away from mu 0, you are going to reject the null hypothesis before looking at the data. This is what happens before looking at the data. So we call this point critical values, lower critical values, upper critical values. So given your belief, you set a certain margin for the random error to happen, and then you set the cutoffs. Those cutoffs are critical values. So once your data are outside, your test statistic is outside of those critical values, you are going to reject the null hypothesis. And then, even without looking at the data, we know the distribution of the data, the sample mean. We know the sample mean is normally distributed around mu 0. If it was true, if the null hypothesis was correct, then it will be normally distributed centered around mu 0, right? That means, so like even if your belief is true, it is possible, like this observation is possible, like you have probability here. So actually normal distribution is everywhere positive. So anything is possible technically, but like this tail is extremely unlikely to happen. I understand that the probability here is really small, so unlikely to happen, but possible, right? That means you already set the rejection region here. Your critical values were here and there, so that means this much area will be rejected, even if the sample average is generated from the correct distribution. This much large, somehow unlucky things happen, so a large random error can happen. So if the random error was too large that the sample average is outside of the critical values, then you have to reject the null hypothesis, because you don't know the distribution at, like, you don't know where the sample average is coming from, whether it is generated from this distribution or another distribution, right? So our analysis is purely based on the assumption that the null hypothesis is true. So even if the null hypothesis is true, this probability happens, which is type 1 error, because any sample average falls on this area will be rejected. Will reject the null hypothesis, which is a wrong decision, right? Okay, this was type 1 error. But type 2 error is similar but slightly different. So now suppose that your belief was here, mu0 was your belief. You believe the mean was mu0, but actually suppose that the truth is mu1. Your belief was wrong, right? If you assume that the truth, if you realize that the truth was here, then now you know that the distribution would be centered around another point, at another point, right? So the distribution is slightly shifted to the right, right? So in this case, because your belief is wrong, the correct decision is rejection. You have to reject the null hypothesis because the truth is here, your belief is here, they are different. They're different. So you have to reject it, but you are not rejecting the null hypothesis if the sample average generated from this distribution is in between the critical values. If the realization is close enough to the belief, you cannot reject the null hypothesis, because you don't know if the data generating distribution is mu1 or mu0. You don't know which distribution is the actual distribution. So you have to reject the null hypothesis if the realized sample average is in between the critical values. So you are going to reject, you will fail to reject the null hypothesis this much probability, right? This is type 2 error. As you can see, type 2 error is pretty huge. Like type 1 error is relatively small. They are tail probabilities. But type 2 error probability is huge, right? But one more thing here is, again, you will easily tell that it depends on type 2 error, depends on where mu1 is. If mu1 was much further away from mu0, like if mu1 was here, then distribution would be like this. So type 2 error would be different. So in other words, like depending on the relative location of mu0 and mu1, it may be difficult to tell the difference between your belief and the truth. In this case, these two values are so close to each other, so you are more likely to fail to reject the null hypothesis. So you fail to detect the difference between the truth and your belief because they are so close to each other. But if mu1 was like far away, far outside the tail, then it would be much easier and the type 2 error probability will be smaller, which is also obvious from the graph. Okay, this is basically the whole summary of what I'm going to do in the first part of this section. Okay. In the next video, I'm going to give an example with more numerical example, and I will calculate the actual probability of this area. Okay. Thank you for watching. I'm going to continue in the next one. See you there.